Okay, let's give you guys some more practice. So integrate this from 0 to 1. So integrate this from 0 to 1. That's this area here. So you don't know how to integrate this. So turn it into a series and then integrate the series. The question is how many terms. The question is how many terms do I need in order to get this area to be within this level of accuracy? So how many terms do we need? So press pause and have a go. Okay, so let's zoom into this bit here. So zooming into that bit will give us this. So we don't know how to integrate this. So turn it into a series. So imagine this as being x minus x to the power 3. So you've got to put this into here. So that will then give you this. So now it's a matter of this multiplying with this. So it will be minus 1 to the power of n, and this times this. So that would be x to the power of 3n. Well, this thing here will equal this. So, hang on. So turning this into a series would be this. We don't know how to integrate this. So let's integrate the series. Well, integrating the series, if you integrate x squared, it will be a third x to the power of 3. So this is always one notch higher than this. So looking at this, when you integrate it, it will be one notch higher. So it will be 3n plus 1. But then you've got to divide it by the very same thing. So you've got to divide it by the very same thing. So divided by the very same thing. So integrate this. That will then give you this whole thing here. Okay. So when you get to this stage here, imagine this. So here we are integrating from 0 to 1. We are integrating from 0 to 1. When you get to this stage here, imagine it as being one fraction, take away another fraction, plus another fraction. You've got to put this into here, put this into here, put this into here, and then take away, and then put this into here, put this into here, put 0 into here, and so on. You see, when you put 0 into here, then 0 to the power of anything, it will always be 0. Well, when you put 0 into here, put 0 into here, put 0 into here, everything will be 0. And then when you put 1 into here, put 1 into here, put 1 into here, it will be you putting 1 into here. So 1 to the power of anything, it will be 1. And blah blah blah. This whole thing here would then be this. So we are trying to work out the number of terms needed in order to get the area to be within our level of accuracy. But the thing is, in order for us to work out the number of terms needed, we need to think about the remainder. So in order for us to work out the number of terms needed, we need to think about the remainder. But in order for us to think about the remainder, we need to show that our series is an alternating series that converges. So the next step is to show that this is an alternating series and it converges. So as always, we would discard the alternating component. We would discard the alternating component and then concentrate on the UN. Concentrate on the UN. Make sure all the UNs are positive, which it is in our case. Make sure all the UNs are non-increasing, and make sure that the limit of UN heads towards 0 as n tends to infinity. I'm assuming you can do all three. So all these three have been satisfied. Therefore, we know that this is an alternating series and it converges. Now we have an alternating series which converges, so we can apply the remainder. Well, there's a theorem that says the remainder will be less than or equal to this value here. Okay, so now let me think. So going back to here, so this is UN, and this is UN plus 1. So going back to here, the remainder, hang on, bear with me. So the remainder will always be less than or equal to the next term here, UN plus 1. So going back to here, the next term will be n plus 1. The next term will be n plus 1. So we've got to put this into here, and then put this into here. So this will be, the denominator will be n plus 1 factorial, and then it will be this 3n plus 3, and then you've got plus 1 here, so it would be 3n plus 4. So the next term will be this. So the next term will be this. So our remainder, there's a theorem that says our remainder will be less than this here. Well, this next term here is given by this. So our remainder will be less than or equal to this. Now we want our remainder to be less than, strictly less than this. This was given right from the start of the video. We want our error to be within this level of accuracy. So we want our remainder to be less than this thing here. So now take the reciprocal, that will then give you this. And then now we've got to search for a value of n where this side will be bigger than 10,000. Well, because of this factorial thing here, we don't have an elegant way of solving this. So let's just guess. So when n equals 4, this whole thing here will be this. Well, this thing here is less than 10,000. We want this thing to be bigger than 10,000. So let's try when n equals 5. When n equals 5, this whole thing here will be this. Well, this thing here is bigger than 10,000. So when n equals 5, it's good. Okay, when n equals 4, it's no good. So so now we now know that we need 6 terms because we start at 0. So now we know that we need 6 terms. 1, 2, 3, 4, 5, 6. So now if you work this out, it will give you this. Now we can be 100% sure that when we use 6 terms, this answer here will be we can be 100% sure that it will lie within this level of accuracy.